Hello everyone, I am Tanu Sharma and this is audio recording for visually impaired students from chapter diazonium salts from organic chemistry. Introduction. Arene diazonium salts were discovered by John Peter in 1858. They have the general formula Ar N2 positive X negative, where Ar stands for the aryl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperature, forming carbocations and nitrogen gas. R N positive triple bond NX negative gives to R positive carbocation plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic applications of arene diazonium salts only, particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, p-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride is determined from analytical data and molecular weight determined as C6H5N2Cl. Grace structure. Grace proposed structure for benzene diazonium chloride in which both the nitrogen atoms were directly linked to the benzene nucleus. Its salt-like character, displacement of both the nitrogen atoms by univalent atom or group in most of its reactions, its reduction of phenyl hydrazine in which only one nitrogen is attached to benzene ring. C6H5N2Cl in presence of SnCl2 or Na2SO3 gives to C6H5NH2. Formation of HO compounds by coupling reaction. C6H5N2Cl plus C6H5. C6H5N double bond N C6H55. Kekulé structure. He proposed a structure for benzene diazonium chloride in which only one nitrogen was linked to benzene nucleus C6H5 single bond and double bond and Cl. Evidence in favor. Structure explain most of the drawbacks of grease structure such as its reduction to phenyl hydrogen, formation of HO compounds by coupling reaction. Point against Kekulé structure. Structure cannot explain its salt-like character and its instability as compared to HO compounds, since both contain N double bond and linkage. Bloom-Strand structure. Bloom-Strand suggested structure for the benzene diazonium chloride in which the nitrogen attached to benzene ring is pentavalent while the other is trivalent. 6H5 and triple bond and Cl negative. Evidence and support. It explains all the objections of structure 1 and 2. It's ready solubility in water but not in common organic solvent. It is completely ionization as shown by conductivity measurements. It is instability as compared to HO compounds. It explains the geometrical isomerism as shown by diazoids. Preparation of diazonium salts. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine. ArNH2 primary amine plus NaNO2 plus 2HX in 273 to 278 Kelvin temperature. ArN triple bond NX negative plus NX plus 2H2O. Diazonium cells are also found when aromatic primary amines react with nitrite esters such as amyl nitrite. The nitrite esters needed for the purpose are prepared by treatment of alcohols with nitrous acid. The C5H11OH plus HONO gives to C5H11O N double bond O plus H2O. General procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. The amine solution is cooled and a cold aqueous solution of sodium nitrite is added slowly to it at such a rate that temperature of the reaction mixture does not rise above 270 Kelvin. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salts. The excess of nitrous acid may be destroyed by the addition of urea. NH2CuNH2 plus 2HONO 2N2 plus CO2 plus 3H2. Since diazonium salts slowly decompose even at low temperatures, they are used immediately after preparation. Evidence in support. The mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. Stability of diazonium salts. Aromatic diazonium salts are much more stable than aliphatic diazonium salts due to the dispersal of positive charge over benzene ring. Physical properties. Arene diazonium salts are generally colorless crystalline solids, highly soluble in water. Many diazonium salts, especially nitrates, are dangerously explosive in dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. Chemical properties. Arene diazonium salts are highly reactive compounds. Their high reactivity arises due to excellent living ability of diazo groups as nitrogen gas N2. They are therefore extremely useful synthetic reagents in organic chemistry. The reactions of diazonium salts are broadly divided into two categories. Reaction in which the diazo group is replaced by monovalent atoms or groups. Reactions in which the nitrogen atoms are retained. Reaction in which the diazo group is replaced by monovalent atoms or groups. Replacement by hydrogen deamination. The replacement of diazo group by hydrogen or the reduction of diazonium salts to arenes is usually brought about by treating a diazonium salt with hypophosphorus acid at room temperature, preferably in presence of Cu salts as a catalyst. ArN2X plus H3PO2 plus H2O in presence of Cu positive gives to ARH plus H3PO3 plus HX plus N2. This reaction can also be carried out by treating amines. It may be emphasized here that during the reaction, diazonium salt with ethanol, two products are usually obtained. The relative amount of two products, however, depends upon the nature of diazo compound and the alcohol used if a first group is present. Replacement of hydroxyl group. Synthesis of phenols. Diazonium salts react with water in presence of acid from phenols. The reaction is generally carried out by adding the solution of the diazonium salt to a large volume of boiling dilute sulfuric acid. ArN2X plus HOH in presence of H3SO4 gives AROH plus N2 plus HX. The acidic conditions minimize the side reaction involving the coupling of phenol with diazonium salt mechanism. This reaction occurs by SN1 mechanism. Synthetic applications. This reaction is especially important since only few methods are available for the direct introduction of a hydroxyl group into benzene nucleus. Replacement by halogens. Different methods are used depending upon the halogen to be introduced. Replacement by chlorine or bromine. Sandmeer reaction. Aryl chlorides and bromides can be easily prepared by treating a flashly prepared cold aqueous solution of a arene diazonium salt with the solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is called Sandmeer reaction and gives aryl halides in 60 to 80% yield. Replacement by iodine. The replacement of the diazo group by iodine does not require cuprous halide or copper catalyst. It is simply achieved by treating a diazonium salt with potassium iodide. Replacement by fluorine. Bausch-Simon reaction. When an aqueous solution of diazonium salt is treated with fluoroboric acid HbF4, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salts, diazonium fluoroborates are fairly stable compounds. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and bone trifluoride. For example, ArN positive Cl negative plus HbF4 gives to ArN2 positive BF4 negative plus HCl. ArN positive triple bond NBF4 negative in presence of heat gives ERF plus N2 plus BF3. Replacement by cyano group. Aryl nitrates can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. ArN positive, triple bond X negative. The reaction is called modified Sandmeer reaction, which is ArN positive, triple bond X negative First, neutralized with Na2CO3. Second, CuCN or KCnCu. Used to ArCN plus N2. Synthetic application. Since hydrolysis gives carboxylic acids, therefore synthesis of nitrile provides the excellent method for the preparation of carboxylic acid from nitro compounds. Replacement by nitro group. Nitro compounds are generally prepared by treating an arene diazone fluoroborate with an aqueous solution of sodium nitrate in presence of copper powder. Replacement by arsenic acid. Bar reaction. Treatment of an arene diazonium salt with sodium arsenite in presence of copper sulfate, followed by acidification, gives an ar- arylarsonic acid. Replacement by an aryl group. Gomberg Baumann reaction. When an arene diazonium salt is treated with an aromatic compound, liquid or its solution in an inert solvent if solid in presence of an aqueous alkali, biaryls are formed. Yields are usually less than 40%. Reactions in which nitrogen is retained. Reduction to aryl hydrogens. Arene diazonium salts upon reduction give good yields of aryl hydrogens. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfide, sodium hydrosulfide, and even electrolytically. AR N positive triple one NX negative, essential to HCl or Na2SO3 gives to ARNH NH2. C6H5 N positive to triple one NCl negative, essential to by HCl C6H5 NH NH2. If, however, strong reducing agent such as ZnHCl is used, the product is an aromatic amine. C6H5N positive, triple bond NCl negative, ZnHCl, C6H5NH, NH2, ZnHCl, C6H5NH2 plus NH3. Mechanism of reduction of diazonium salts with the sodium sulfide. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atoms, forming the dianion of hydrogen sulfuric acid, which is then converted into hydrogen in presence of acid. Coupling reaction. Arene diazonium salts react with a highly reactive aromatic compounds such as phenols and amines to form brightly colored azo compounds. This reaction is known as coupling reaction. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction, in which diazonium ion acts as an electrophile while phenol or amine acts as nucleophile. Coupling with phenol. Since benzene diazonium ions are only weakly electrophilic, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxadiene is strongly nucleophilic, therefore coupling reaction of phenols are usually carried out in alkaline medium. Role of pH. The pH of the medium plays an important role in the coupling of phenols. As stated above, coupling of phenols is carried out in the weakly basic medium as explained above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to diazo hydroxide, which further reacts with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in the equilibrium as shown below. Coupling with amines, tertiary amines. The mechanism of coupling reaction of diazonium salt with tertiary amines is similar to that of phenols, except that this coupling is carried out under weakly acidic conditions. Reaction with primary and secondary amines. Coupling of diazonium salts with the primary or secondary amines occurs in neutral or mildly alkaline medium. Here, NH2 group of the amine first attacks the diazonium cation to form diazoaminobenzene. However, when diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoamino amino acid rearrangement to form p-aminoacidobenzene by the following mechanism. Role of pH. In the presence of a high concentration of H positive ions, the lone pair of electrons on n atom accepts a proton. As a result, the amine exists predominantly in the protonated form as shown below. Due to absence of lone pair of electrons on the n atom, the amines is no longer nucleophilic and hence the coupling reaction will not occur at a high concentration of H positive ions, that is low pH. Further, as explained above, too high alkalinity, high pH will also not favor coupling reaction by forming unreacted diazohydroxide or diazoate salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for such coupling reactions. Thank you.